Okay. Hello, everyone. I'm Wei Wu from the University of Science and Technology of China. It's my great honor to introduce our work titled Adaptive Feature Decorrelation Graph Collaborative Firing for Recommendations, abbreviated as AFDGCF. In the era of information overload, recommendation systems have become essential in various online applications by providing personalized item recommendations. Among the popular techniques, collaborative firing stands out for its ability to derive meaningful user and item representations from the historical interactions. Within the collaborative filtering methods, graph neural network-based collaborative filtering is currently one of the most effective approaches due to its ability to capture high-order connectivity between users and items. Despite their effectiveness, GNN-based graph filtering models still face challenges due to the use of graph neural networks. These challenges include issues like oversmoothing and feature overcorrelation. In the context of GNN-based CF models, a single GNN layer predominantly considers the immediate neighboring nodes of users and items. To capture deep collaborative signals, conventional GNN-based CF models stack multiple GNN layers to expand their receptive fields. However, as the number of GNN layers grows, the similarity among presentations of different nodes increase, which is known as the oversmoothing problem. Simultaneously, the correlation among feature dimensions in node representations also increases, which is refers to the feature overcorrelation. Oversmoothing and feature overcorrelation share similarities, as both become more pronounced with an increase of GNN layers. However, they also exhibit distinct difference. Oversmoothing is viewed from the node perspective, while the feature overcorrelation focuses on the feature perspective. Next, we would like to introduce some related works. As graph neural network began to be applied to collaborative filtering, many excellent works have attempted to make GNNs more suitable for CF tasks, focusing on the structure of GNN models. Additionally, some works focus on the oversmoothing problem. One category of the model aims to streamline the process of message passing, like GCN, GCCF, and Ultra GCN. The second set approach performs feature propagation within the subgraph, like IMP, GCN, and SGCF, which divide the graph into several small subgraphs. Besides the efforts to alleviate oversmoothing, it's noticeable that oversmoothing may not invariably be bad to recommendation system, as some research shows that the smoothness of embeddings plays a vital role in the effectiveness of GN-based CF models. Although significant progress has been made in research of oversmoothing, there is currently a lack of study on the overcorrelation issue in GNN-based CF. In this paper, we analyze the impact of overcorrelation issue on GNN-based CF models and propose a suitable solution. Before diving into the specifics of our methods, we need to understand the more preliminaries. The measurement of overcorrelation and oversmoothing is fundamental to our study of these two issues. In this regard, we follow previous research in the field of graph neural networks using COR and SMV to measure the extent of overcorrelation and oversmoothing. COR calculates the average correlation coefficient between any two feature dimensions, where ρ denotes the Pearson correlation coefficient, and SMV computes the average normalized Euclidean distance between any two nodes, where d denotes to the normalized Euclidean distance between any two vectors. This basic basic formulation of GN-based CF is likely similar to everyone here. After each layer executes message passing, we obtain a layer representation matrix, and the final representation matrix used for similarity recall often employs jump knowledge, pulling the representation matrix for each layer. Based on the measurement of overcorrelation and oversmoothing, we conducted an empirical analysis of 4 representative GN-based CF models using moving length datasets. From the figure, we can observe that the following trends for these 4 models. Firstly, COR increase with the larger counts indicates an increase in correlation among the learned data representations. Secondly, SMV decreased with layer count, indicating an increase in the smoothness among the learned representations. Thirdly, the recommendation performance doesn't consistently improve with the increase in number of layers. Instead, the performance degradation occurred after reaching 2 to 3 layers. The above 3 points reveal the widespread extent of overcorrelation and oversmoothing issue in GN-based CF models, leading to the suboptimal performance of the model. Moreover, the severity of both issues increase with the number of layers, indicating a certain association between them. Next, we will analyze their associations theoretically and propose solutions. Firstly, we need to provide a definition for row and column correlation of metrics. Generally, when we calculating this correlation coefficient, it's standard practice to normalize the metrics to have a mean of 0 and a variance of 1. For simplicity in our analysis, we assume that the representation matrix E satisfies double standardization, meaning each row and column of E has a mean of 0 and a variance of 1. Under these assumptions, we define the column correlation coefficient matrix PC like this. PC of E as follows. Each element PCIJ in the matrix represents the correlation coefficient between the i's and the j's column. Similarly, the row correlation coefficient of E denotes as PR can be defined too. Based on this, the column correlation and the row correlation of matrix can be described by the F norm of PC and PR respectively, which can be considered proxy for feature overcorrelation and smoothness measurement. This is illustrated in the figure on the right. Then we have the following theory. If matrix E satisfies double standardization, then its corresponding row correlation matrix PR and the column correlation matrix PC are proportional in terms of their F norm. A brief proof process was displayed on the slide. The above theory reveals a proportional relationship between the column correlation and the row correlation of a matrix. Therefore, we can conclude that the overcorrelation and oversmoothing are positively correlated in degree. These findings align with the observations from the previous experiments. Based on this conclusion, we can use the following proposed method to address the issue of overcorrelation while mitigating the impact of oversmoothing. To address the high correlation in feature dimensions of user and item representations, a straightforward approach is to include a loss function that controls this correlation. So our goal is to decrease the average correlation between the column of the presentation. Formally, this can be expressed as P hat C. Since the correlation coefficient of a vector with itself is always 1, we can simplify the P hat C further using the previous defined column correlation coefficient matrix PC, where the PCIJ can be computed from the corresponding covariance matrix, and E hat represents a matrix composed of the mean value of each column of E. Although directly applying P hat C is a simple and effective baseline strategy, it may not be the optimal choice. One critical consideration is the different pooling strategy used by various GN-based CF models. For instance, GCCF employ concatenation, whereas LGCN use mean pooling. This results in significant difference in the correlation of the representation matrix E across different models. To address this and ensure our approach remain model agnostic, we propose an alternative approach that is penalizing the representation obtained after each message passing operation. Furthermore, due to the substantial difference in user and item feature distributions, applying penalties separately to the user and item representations is necessary. This approach also helps preserve the relationships between the user and the items learned by the model. Additionally, since feature smoothness contributes to the effectiveness of GN-based CF models, it is crucial to maintain smooth representation in the deeper layer while control the feature correlation in the model's final representation dynamically. Therefore, we propose adaptive penalization at each layer based on their relative correlation magnitudes. Finally, the form of our feature decoration loss with the adoption of the adaptive strategy, the penalty coefficient for user and item changes at each layer in every training step. Notably, we do not impose a penalty on the repetition matrix of the zeroth layer. This is because the zeroth layer represents the initial user and item embeddings, which was not undergo which have not undergo graph convolution and are usually subject to the L2 regularization constraints. The final training loss consists of the origin loss function of the CF models and the AFD loss. The hyperparameter alpha controls the relative size of the AFD loss. Next is the experimental section. First, we will introduce our experimental setup. We select 4 publicly available datasets to evaluate the performance of our proposed AFDGCF, which varies in domain, scale, and density. The dataset statistics are shown in the table. To evaluate the recommendation performance, we select recall, NDCG, and MAP as the evaluation metrics, with K set to 10. Regarding baseline models, we choose several state-of-the-art models, mainly including 3 types. Performance comparisons are shown on the table, demonstrates the effectiveness of our proposed AFDGCF. The table reveals that implementing AFD loss in all the aforementioned GN-based CF model is effective. This stems from notable performance enhancement achieved by mitigating the over-correlation issues while successfully balancing the mitigating over-smoothing and maintaining embedding smoothness. Recent studies have indicated that GN-based CF models like LightGCN are much more difficult to train than the traditional MF models. These models often require a larger number of epochs to reach the optimal state. We hypothesize that the issue of over-correlation and over-smoothing diminish the distinction between positive and negative samples, thereby impacting learning efficiency. Fortunately, we found that our AFDGCF framework can alleviate this phenomenon, and evidence in the table about the comparison of training efficiency. For the ablation study, a key component of our proposed AFDGCF is the adaptive strategy. The experimental results are present in the right table, where AFDF denotes applying a fixed penalty coefficient of 1 over a number of layers to each layer. Clearly, we can observe that our adaptive approach consistently outperforms the fixed one. Across all GN-based models, demonstrates the effectiveness of applying varying decorrelation penalties to distinct layers. In our AFDGCF framework, hyperparameter alpha balances the CF task loss with our proposed AFD loss, acting as a regulator for the intensity of decorrelation. This figure reports the performance as alpha varies. We can observe that setting a appropriate alpha can markedly enhance performance of our methods. In the case study, we investigate the effectiveness of effects of our proposed AFDGCF framework using LightGCN and Hamlet. We find that our method improves the performance of the model with different numbers of layers. The greater improvements observed as the number of layers increase. From the COR and the SMV metrics, it is evident that our proposed method can alleviate the over correlation issue by constraining the column-wise correlation of the repetition matrix while simultaneously reducing the row-wise correlation, thereby mitigating the over-smoothing problems. In conclusion, we would like to briefly summarize the advantage of our method. Our method is easy to implement, can be plug and play with existing models, and is orthogonal to other improvements on GN-based CF models. We hope it can advance the development of GN-based CF in conjunction with other excellent works. Yes, that's all. Thank you for listening.